Hi, it's quite a long time since the last video. I had a couple of major UI updates that I wanted to finish first before I proceed with new tutorials, so I don't need to change everything after it. So you will notice that the older videos look a little bit different in the UI. Also, some nodes have more settings. There are lots of new nodes, new features, etc. But this is not the topic of today. Today, I want to show you in step-by-step way how to generate custom G-code on Gerridaj. So I would say we first start with having a look into some examples into the public workflows, and going from there we will create some custom G-code which you can actually print, or you can simply learn how to do it using this node-based editor. In this example project you see a mix between normal STL files and also G-code, so you can imagine this here as just an STL which you can download, slice in your favorite slicer software and print it. These are just demos, so maybe some of them are not easy to print, but I wanted to show what you can do in very quick way and with this software in terms of parametric modeling, so you can quickly change many things here. For example, this is the corner radius of this base rectangle which builds the strips. You can change the modulation of the strips and so on. So you can just play around with all the settings, then download the design and try to print it, or actually print it. So many of them will work. This is normally there, but it's also built in a parametric way. If you load it into the editor, you see everything is done with same nodes, which you also need for G-code generation later on. Of course, G-code will need a couple of nodes more. Let's go back to the public projects and let's grab one with actual G-code. So we will take a simple one for the beginning. For example, this one. This is just a flow rate modulation. So basically this is normal cylinder shape going spiraling up in base mode, but changing extrusion constantly in sine wave function, as you see here. And you can also twist it a little, so the different extrusion values are visualized here by color. So red color means more extrusion. That's it. And this is very simple to do. You see, you only need 4 or 5 nodes for the basic shape. You still cannot download the G-code here, because for that you will need a machine node. Double click for search activation, and then you can just search for machine and grab the machine node. So, and you see, this activates the default print area. The shape is quite large, so we will need to scale it in order to increase the print area, but the print area is depending on your printer which you are using, so you can just set the settings here. But this is going to be chaotic, I notice now, so let's do it a little bit more systematic. So first of all, I noticed in my previous tutorials or also Reddit videos that many people are kind of over-respectful regarding G-code. So this is kind of, I don't know, a mysterium for many people, and maybe we need to explain a little bit of G-code first, what it is and what it does. And in order to do that, let's generate quickly some basic G-code, and then I can show you. Or maybe let's grab existing one. It will be faster. So let's take a look into some G-code generated with Cura slicer from a model I created for LED clock. It's not that important, but here see, it's basically what it is. It is text. So it is normally human readable text. It is nothing encrypted. And it has a very simple syntax. So it's very easy to understand by human actually. The beginning, you see some lines beginning with semicolons. Those are comments. So these are ignored by the machines. This is pure information for the reader, which parameters or which slicer was used, etc., which flavor. So flavor is the first mysterium many people are confused about, because in the 3D printing community, many people think that flavors are somehow important or very different. This is actually not true, because about 90% of G-code which is used even in different flavors is actually the same. So, and flavor differences are mostly special commands, some special macros used by your machine, and these are usually not part of your actual toolpath. So normally your flavor differences are some kind of pre and post processing commands. So first of all, I will divide it into some sections. So we put here some lines and some comments, because here after these lines begins the normal toolpath itself. This is your geometry, which will be printed actually. And what happens before that? Those are pre-commands. So some setup of temperature of the bed, temperature of the extruder, etc. These are standard commands. These are absolutely identical among all the different flavors. Sometimes you encounter different commands which are special for that flavor, but you need them once in these pre and post commands usually, and then you can just replace them. Sometimes tool changer commands vary also from machine manufacturer to machine manufacturer, because some 3D printers use a standard command, standard CNC G-code command for tool change, and some other machines use a micro for that because they need to perform some more actions, actually extrude something, length the nozzle, etc. before the actual change command. So these might differ, but you will notice, first thing you do if you design custom G-code, you can look into your normal sliced file, try to separate these sections first. So what are your setup and preparation commands? So then you have these sections. These are commands which you will need anyways. So you will need to home your machine, you will need to set up the temperatures, turn on fans, etc., do some pre-extrusion, and so on. You can just copy those commands directly into your text file, or you can set up them later in the machine node. I will show you how later if you are in the machine node itself. But this is important to understand that these flavors are actually not important at all. So most G-code is exactly the same most of the time. And if you have some differences, then you will notice that it's not that dangerous. So you can break some things if you do very, very, very strange things, like, I don't know, driving your nozzle into negative values or something and hit your print bed. You need to understand a little bit of coordinate system, which goes on here. So if you see, these G1 commands are extruded movement commands. If you have this extrusion, it's a special case for 3D printers. In normal CNC, you have not this extrusion command. And instead of that, it just moves your milling bit, for example. And then to G1, you have also G0 command, which is normal travel move. In case of 3D printing, it means travel or move without extrusion. Yeah, okay, so different feed rates are basically different speeds. So you can set here the speed, and this goes on as long as you are not changing that command later on in the next line. So and what is G1 command means, it's go to this X, go to this Y, and keep the previous Z, which is 0.2 because that is not changing, and extrude that amount of filament. So you see this pattern is going on, go from one coordinate to the next coordinate and extrude some amount of filament. And eventually you will notice a layer change if you search here for Z. Next one. So here's the next layer change. We are going to Z0.275. And this is our next layer, if you print layer by layer in 2D printing, actually. So, and then you have the same, setting up the feed rate, going to a point, extrude some amount, go to next point, extrude some amount. And this is what we need to know. So the G-code is actually, the actual toolpath is constructed out of a bunch of points and some extrusion. And that's it. You just need to write this text in some way to get out something printable out of it. You can, of course, design some motion paths with this knowledge, which will result in extrusion in the mid-air, not sticking to the bed or going straight up, for example, in Z, and the machine will perform this movement, but nothing usable will be printed that way. So you need to find a way how you can organize these points so you can actually print them in a way that they are creating some shape and also sticking together. And this is what the slicer does for us. So slicer software creates this G-code from 3D mesh. So it takes a mesh, an STL or 3MF file, and slices it into thin layers, and then defines the points where the printer should go and the amount of how much filament to extrude. So very simple, actually. But the slicer normally does only layer by layer 2D paths. So as you see here, you have one step in Z, and then you have many steps in this new XY plane. Then you go to the next layer, next Z step, and then XY layer again. This is what builds this visible seam, this Z seam. This comes from the Z steps. And this also eliminates any possibility for non-planar prints, for normal 3D printer, which are actually capable of. Of course, you have restrictions with nozzle clearance, and you can hit the part itself. So fully automated non-planar printing and slicing is actually quite hard if you want to fully automate it. But what we will do with Gerridaj is not fully automated. It's kind of manually constructing your G-code, but with help with some automation. So it's kind of mixed. And this allows for some creative use cases, for some artistic use cases, which you will see later. Okay, and then we have, of course, also the end part of G-code. Let's see. So a bunch of comments in the end again. And then we have here still movement commands, some M, 204 command, and that's it. So here we are done. This was the last extrusion command, and here we are homing, setting extrusion to absolute mode, and turning off the fan. So that's it. This is the entire G-code. just line by line text, some points, some commands. I hope it helps you to demystify it a little. So in terms of machine compatibility, most of G-code is 100% compatible to any machine. If you take care of your coordinate system, so you need to be in the coordinate system of your printer. This means knowing the 0 point of your machine, knowing the print area, and use these post and pray commands in the right way. So this may vary from machine to machine, but the rest is usually the same. There are some specialties. So some machines, normally CNC machines, also support arc commands. So you can create circular motions without defining a lot of points for that. So, but this is normally not used in 3D printing. So I did not see any slicer doing that. So normally a slicer creates any circle by just creating a bunch of points on that circle. Yeah, there's a specialty with Delta printers, for example, regarding coordinate system, because the 0 point is in the middle of the plate, which means you will need to set in the machine node, you will need to send your 0 point to negative coordinate. Yeah, okay, this is G-code part. Let's go back to the editor. So we saw we need a bunch of points to create some kind of G-code. So we need coordinates. In this case, let's disconnect everything. We start with a circle. But a circle, let's deactivate the grid here. In our case, the circle is actually a polygon. If I define less segments here, then you see this is a polygon. And this is like every mesh is constructed. This is not mathematically perfect definition of a circle, which you would have in a normal CAD software first before it's translated into a mesh. We don't need it here because we want to work on a mesh and with points at the end anyways. So therefore I decided to use finite discrete data in the first place. So, okay. And if you look at the points, which you can do with the points viewer, you see these are the points which you have. And actually you could even already print this. So you could print this polygon if you needed to. It's not very useful, but you could define this toolpath, which means go from that point to that, and then to that, and then to this one, extrude some amount of filament in the between part, and then you will create this shape. You will also need to define a height of that. So if you don't have set a Z offset on your machine, then you can just put your toolpath directly into some different Z. So I can put it into 1 centimeter height. You see, and you could even put that into your machine, and the machine will execute this command. The filament will not stick to the bed because it's too high, but it will drop just on your bed. If you, of course, you see your 0 point of the machine is here now in the middle of the shape. So this will not work. You need to move the shape into your print area first. And to do that, you use either, you can just do it here with moving the center point directly. In most nodes, you can do it directly in the nodes. And we are already in the print area. So, and now I will show you that G-code will already be generated if we connect it to the machine node. So we grab the machine node here, connect it. You see we have the print area settings. We can leave it by default, the origin coordinates as well. Here you can provide some extrusion settings like in a normal slicer. But what is important to know about machine node here, settings about layer height, extrusion width, etc. They are not affecting, of course, your geometry. So the real layer height is defined by the geometry itself, by the curves and by the points which you design. These values here are only used internally by the node to calculate the correct amount of extrusion for your nozzle size and your layer height. That's it. You can define a different layer height in your geometry and here, which will result in some kind of wrong extrusion. You can specify here the extrusion mode in absolute and relative, which you also can do in the pre and post commands later on. You can define the most important values here, which are needed for any kind of 3D printing. So you need to have to set the speed, temperature, and so on. These are the basics. So, but this should be known from all other slicers. In pre and post command section, you can set the pre and post commands, which I showed you in this G-code. This is what goes before. It is before section, before the actual toolpath starts. So we have the first command here, which sets the units to millimeters. Okay. This is important, but I guess most machines have it as a default setting, but you can just keep it here. Then you can have here this absolute positioning, which is the same. Oh, no, it's not the same. This was the extrusion mode, but the extrusion mode is also here somewhere. No, I deleted it already, but you could define actually also the extrusion mode here as a pre-command. This will be added automatically by the node. So you see here some pre-commands which I use for my machine. So I use absolute positioning. This is important for yeah, in most cases for your geometry itself. But for example, in the end, if you are done with the print and you want to go to the safety height first before homing, then you can, for example, switch to relative positioning and add a Z5 command, which means it goes then 5 millimeter from your last position. That means relative. It goes not the Z height 5 millimeter, it goes from the last Z position plus 5 millimeters. That's the difference. Then you are above your printed geometry. Then you can home, and then you can switch back to absolute positioning. Or you go first, you go up, then you switch to absolute positioning, and then you go home to 0, 0. So that's it. So I turn off the fans in the beginning. This is the temperature. It uses variables from settings. Yeah, wait for extruder to hit. So some standard commands, which you will later see into G-code. Home all access and rise the head before start. So I don't want to hit any parts of my print bed. Therefore, I rise the head always before the start. You can add new commands here, and you can also remove commands here. Okay, let's see. Let's have a look into G-code. So you can directly download it here. This node is a premium node. With a normal basic account, you can only download it if you have enough credits, which you can earn in community projects, which I will explain another day. But okay, let's say you have the ability to download, and you always have the ability to preview your G-code. So let's take a look. We have 5 points. You see here. These are 5 points from our polygon. These are our comments with the settings we defined in the tab before. So the speeds and the temperatures, etc. And here are our pre-commands. So this is what you define in your pre-commands, which is before the toolpath begins. And here we have the begin toolpath. I have this M82 command extra here. This is because you can do it as a pre-command, and now you can have it as a setting. And in order to always to use the setting, this is part the last part before the toolpath command, which overrides anything which you define in the pre-commands. This means if you have some wrongly defined configuration of machine node from your previous prints, where this command was setting the relative mode, and then you want to change it to absolute mode in the settings, this will work because this comes after all pre-commands and overrides it. So it's just a safety mechanism so that the setting always takes priority. That's it. So now we have our G-code, which will print our geometry. You see here, we move to start point, which is, as you see, at Z is equal 10 millimeters, which is quite high, and it will just print at this height. These 5 points with the extrusion values calculated for your nozzle and layer height. And then we are already at the end. So this is a very short G-code, very simple G-code, which will not print anything useful, but the machine will accept it and it will work. These are the basics. So now you know how to create very simple, not very useful G-code. And so now we can go on and start to think about how we can make it a little bit more useful. So in Gerridaj, you can create G-code directly from curves or directly from points. So you can even grab a point here and start designing with a point. So you can add multiple points now and start doing something with that. For example, you can grab a distribute node and create some more copies of the point. Let's say 5. And let's take a look. Now we have 5 points. And if we translate it to the print bed and print it, we will achieve the same, because this is actually also 5 points. Maybe they are rotated a little bit different, but it's also just a polygon at the end, created with points and visualized also as points and not as lines. Of course, you will normally need a couple of more points. So let's say you take 500. Now it looks much more like a circle. You have a very small distance between the points. And this can also be used to generate G-code. Of course, this is also just a circle, not very useful. You can take another distribute node and create some more layers now. So this way, in this case, you need to choose Cartesian, and in counts, how many layers do we want? Let's say we need 15 layers, and we need a distance of layer height in this case, because we will now distribute in Z direction. So we are creating now layers. Let's say we want 1 millimeter layer height because we have a big nozzle, and we go in Z direction. So now you see, okay, the points are quite large now. If I take the points viewer, I can decrease the size of the points. It's better visible. So now you have equally spaced points in multiple layers. So in this way, you could print a cylinder already. So a wall of a cylinder, so cylinder in base mode. This is a very basic design, which is still not very useful. But that way, you design your G-code by points alone. So in order to make it a little bit easier, you can start with curves instead of pure points. So you can just take a circle and then start with a circle, because you will need less nodes and go faster with your design. So you design here how many segments you want to have, and if you need a cylinder, then you can just extrude it into a cylinder. It's like a normal cut. You can extrude here a curve, a closed curve, into a shape. And in this case, this shape is a cylinder. You can define a couple of more segments so it's smoother. You can define as many as you want. It depends on your use case. And if you activate here wire mode, you see this is a normal mesh. You could download this mesh now with export mesh node and slice with normal slicer software if you wanted to. Or you can now find a way how you get the points from this mesh. So it's like a reverse process. So here we have seen how to design from the points first, and here you see how you create a mesh first and then you get points. This is what slicers also do, but we will do it in a little bit different way. So because we're normally interested in, let's say, in artistic cases of lamps and lampshades and vases, you actually need normally only the outside vase mode path and not the inner parts of the shape. And then you can just use spiralize mode, which gives you similar path which you will get from vase mode and normal slicer. But you don't need to switch to another software, you can do everything here. And now you have the spiral. And here you can define also your layer height. Let's say we want 1 millimeter. So here you have a continuous spiral. The difference is now to the points we've seen before. The step, there's no discrete step in Z. There are now a lot of discrete steps in Z, but in each point. So each point goes a little bit higher. So we have a continuous spiral without a visible jump layer per layer. This will create a spiral which has no seam. So now you could print this. So it's also very basic shape, which is not very useful, right? But this is the basic technique which I use for my design. So what I normally do, I create a basic shape as a mesh, and then I get the outer path of it, and then I also modulate the path. So if you are into custom G-code where you want to do something interesting or something more interesting with your paths, you can start to modulate your curves in some way with mathematical functions, or in any way you want actually, but mostly I use mostly mathematical functions. It's very easy to do actually. You can grab the curve mode node, connect it to any curve. In this case, it's to any geometry even, but if you want to create G-code, you need either points or curves. If you do it with mesh, this will take the points of your mesh, and these are very few points which are not properly connected in the height. So this will move your machine somehow, but it will not print anything meaningful. So we connect it to the curve mode and activate the preview. You see it already does something. So because we have some default settings in each node, you can see here basic modulation is set. Let's change the layout so we have a bit more space to display the things here. So curve mode. Basic modulation is set to sine wave with this frequency and with this amplitude. We can change any settings. So you see it's a little bit strange here. And why is this that way? So the curve which we put in our curve mode node now is one single curve. So and it is treated that way because you can also put many circles here, and it will look different. So what this means that this frequency is applied to the entire curve, and you see you have here 10 picks in the entire curve. And this is normally not what you want mostly with your spiral paths. So and most of the times you will need this frequency applied to one single turn, and to achieve that you can just check in this frequency per turn checkbox, and this will change the shape. And now you see you have this sine modulation applied to each layer in your spiral. And now you can change everything. You can change the frequency, you can change the amplitude, you can change the direction in which it goes. So you can, for example, do it with Z. Imagine you do non-planar printing in Z, but let's see what you'll get. Yeah, this will hit your print bed, as you see. Check in adjust height for Z. And what it does, it puts each layer to the height of the max height of previous layer. This will not stick together because you see the picks are not connecting here. But this feature is for these use cases when you want to print some gaps and you want actually to go pick to pick. So you don't want to connect the lines continuously in any point. You want to connect only some of them, and this it's better visible if you turn on the alternate block here. You see here now the tips are connecting. So and this is this will be not easy to print because you have gravity. The filament is flexible. Filament is not dry usually if you print it, so it's affected by gravity and it's just falling down. So in order to print in such ways, you will need to print very slow to cool down as fast as you can, and actually print also at the lowest possible temperature, so it does not need that long to cool down. Also, you can decrease the amplitude. Of course, 1 centimeter is quite high. If you decrease it, print slow, and cool fast, then it will actually work. So, and you also need to take care of your nozzle clearance, because if you do too much of non-planar movement, too much of that movement in your print path, you will hit already printed areas with some part of your tool head or with the nozzle, etc. So there is some experimentation involved into all of this, so you need to try things out here in order to make it work. I would also not recommend to start with Z modulation in the first place. Much easier is to do something in the plane of the curve itself, because now everything stays separated properly by height. There's gravity cannot do much here, and you see what you print here. This is kind of double walled spiral now, which will create a pretty robust shape actually. So normally if you print something, if you print a cylinder in vase mode, this is not very stable. You can just squeeze it and everything breaks apart. If you print it that way, it looks quite interesting, and it's also quite robust. So I tried it a couple of times already. You can see some example on Reddit, maybe one day also on YouTube. Yeah, this is it. So you can change the function type. So you can go from sine to triangle. There's all sorts of things you can change here. You can do even a custom function here. You can just type in some kind of formula you want to use, and it will create the points for you. It can happen that your spiral have too few points to modulate, because let's see, every curve is actually defined by points. You see this spiral as well. This is a bunch of points. And you can define how many of them you have per layer here in the spiralized node. So if you have too few, then some functions will be not very smooth. So for triangle, because it goes in straight lines, you see, it works. You can just displace this point and displace this point, and it's still a triangle. But if you switch now to sine function, for example, a sine is normally a smooth curve, and it needs a lot of points to remain smooth. So if you do that, you see the sine is also a triangle in that case. This is only because you have too few points. If you increase the number of points here, now it's looking much more like a sine function. And you can achieve that in many ways. So sometimes if you have a very complex shape and very small layer height and very large number of points, the spiralized node will take quite a lot of time. So let's try to demonstrate it. We do it with these settings. You see, it's already needed 4 seconds to calculate it, because we have very, very many points and very small layer height. You can do it. It's actually not that painful, but normally you can set it to a reasonable value here, so it's much faster, less than 1 second in this case, and then you can still do some resampling in the curve mode. This is extra for this use case. Let's say let's do it so it's visible. Let's go to 100 back. So you see it's triangle. It has not enough points in the spiral, but if you do resampling here, then it's much faster and it still creates a smooth curve. So this is done in order to make your workflow more efficient. So you can, so your parametric design works much faster than it would be another way. So, okay, these are basics of the modulation here. Let's see, whether we have something important here. Forgotten. Yeah, there are some settings here which you can play with. So fade in. This means it starts smoothly to modulate your curve. You see it here, it starts straight and then it changes into your function. Also fade out. You can set the distance, how fast it goes. You can set some pattern effects. For example, this alternate means the function flips direction. And the block size means how many times to repeat in one direction before the flip. So now we have 5 layers before we flip, and this will create some gaps in your texture, and this is very useful, very nice looking structure for vases and lampshades. So it does not create a solid piece of bound plastic, so it creates real gaps. Let's do it more drastically so you can see it better. So this is what it does. You can add some skip pattern. This means it just does no modulation at all for some number of layers, and you can do it between blocks. So in this case you have 2 lines in between your modulated lines which are not modulated. You can set it to 5. It's sometimes very useful as well to avoid any seams. So the problem is with the alternation functions, at some point in your spiral path, you need to change the direction, and the direction change is actually a non-continuous thing to do mathematically. So it's very hard to avoid all the seams in all constellations here. So in order to prevent a visible seam, sometimes in some constellations it's very useful to add this skip button, and you will see in this case you will not find any seam because it's connected seamlessly. So you can turn it as much as you want. Maybe if you look very carefully, you will find the place where the trick is, how to avoid it. But yeah, there is, in this case, no visible seam at the end. It's quite useful. What else? Yeah, this is quite powerful node. Actually, you can do a lot with that, especially if you start to define your own offset functions for your points. You can end up with very creative, nice looking designs at the end. Yeah, that's it. You could already print that. So this is already a little bit more interesting than just a cylinder, right? But even that is actually too simple, right? You need some more interesting shapes in the first place before you do all these kinds of modulations, all these kinds of patterns and so on. So let's see how we can do more interesting things. So you see extrude is just straight extrude, so that's pretty boring actually. Let's remove all the nodes here and start over with a circle. But in this case, we will introduce the number series node. And number series node creates just a bunch of numbers. You can define start value, so the first number in the series, the amount of numbers you will need. This is the count value, let's say 100, and the step. So the step, in this case, you can choose your layer height, or you can choose any number. You can also calculate which value you need in order to achieve a certain height of your final shape, for example. So if you do it that way, 100 times 0.1 will give us a cylinder of height of 10 centimeters, for example, if we connect it to the center position. But you can do it, you cannot do it directly. See, it's not compatible. You need a vector first. Let's grab a vector and connect the vector to the center. It's still at 0. And now, if you connect your number series to the Z coordinate, you see it creates automatically 100 circles with that distance of your step. So, and okay, now we have different heights. But different heights, this is actually the same what we could achieve with the extrude node. So we actually don't want just different heights. We want to have different radii of our circles. So let's take a copy of the number node and connect to graph mapper. And this is very, very, very powerful node. It's one of my favorite nodes actually. So you can here connect number series to graph mapper, and it will give you another number series. So here we have incompatibility between the numbers. So we have 100 here, and we have the default 10 here. Every time you see this choice, this means you need to do something about your input matching. So if it's intentionally that you're working with different sizes of your lists or number ranges, then you can change it in the input matching, and then you can choose what you need. So you will need these settings only if you are more advanced user of that and you are understanding what you're doing here. So the shortest list is 1 here, and just creating 1 circle, and longest list will match the longest list, which is the 100. But this is not what we want. So we want to change it to default, and we want to match by the input. So you have 100 numbers here, and you need also 100 here. And then it will work automatically. So what we have now, we have 100 circles of different radius at different height. So now you can also define your step. You will probably not need 100 centimeters of radius, and your minimal radius is probably going to be something reasonable, let's say 3 centimeters. So what we have now, we have different radius and different heights. So with the graph mapper, you see it's going linearly, increasing the radius, but now we can change it. We can change it into any shape you want. So this is like magic. So now you can see we have already some kind of a ball. So very simple shape and instant visual feedback. So with that node, you can create lots of variations of your shape and iterate quickly. And yeah, this is very, very, very nice thing to have. You have here different functions which you can use for the mapping. So Bezier is a very powerful one because you can define the shape in a very natural and intuitive way here. But you can also use polygon here. If you hold down Control key and press mouse, left mouse here, it will add a new point here, and you can add as many of them as you want and create shapes with sharp transitions. So Bezier gives you smooth transitions, but you can also have sharp transitions with the polygon. Actually, you can also add points in the Bezier, so with the same way. So just hold down Ctrl key and place left mouse button, then it will add some new points. So there's actually a way to remove them somehow. I'm honest, I've forgotten how to remove points here. It's Alt and left mouse click on the point, it removes the point again. So now we have it. So you can add Control and mouse and remove Alt and mouse. So that's it. So you have lots of functions here, polygon, some map functions, sine, where you can change the amplitude, the frequency, the phase, and so on. You have exponential, you have somewhere logarithmic, you have an arc. Okay, that's the parabola, but somewhere is the arc. The arc is also a very useful one. You can just play around with the node. It's I guess this will be one of the most used ones. Yeah, together with the distribute node, probably. Okay, but let's say we want to have a ball or some kind of flower pot or something. Shape is actually already some kind of interesting. So this is going to be just one example. So we do not try to win a design contest here. Let's say you want to have such a ball. We have now base shape. Actually, you could set the steps in your number series that way that you have already your desired layer height, and set the resolution or number of segments in your circles to a reasonable value, so it does not look too much like a polygon. And then you have already lots of points which you can use to generate G-code. Let's reduce the size here of the points. So you see there are some, okay, we have quite a large distance here, it's 1 millimeter. It creates here quite a large gap. It will be probably not printable that way, because the lines are just too far apart and will not stick together. So you need to keep in mind that you can create some designs that will be not printable that way. But if you do it correctly, if you adjust something here, less curvature, so bring the lines closer together, add some modulation so they stick better together and so on. So you have full control here over everything, so you are also responsible for printability of your design in the end. Okay, so you could do that. So you could use already the points directly here and print it. You can also use a loft node and create a mesh first. So you can connect your contours to a surface and then spiralize it or slice it with the slicer node and redefine your points. So what you will achieve here with these lines, you see they are on constant heights. So you will never achieve a seamless print with it, because it will create a Z-seam, because you need to jump from one layer to the next layer. So in order to avoid it, you need to spiralize node, which is going constantly a little bit higher at each point, avoiding a seam. So that you can do with the loft here. Loft gives you a couple of options. So you can close the shape, so it's kind of a closed surface in this case. You can increase the number of segments of the loft, because you see it's quite of low resolution here. In order to improve that, you just increase. Number of triangles are used by the loft, and also you can do some interpolation, adding more curves, and you can also use some smoothing and smooth your load further. I see this kind of bug here with cupping in the smoothing. This needs to be fixed later. But if we are going to make our ball with, we don't need the cups anyways. So let's ignore the bug for now, deactivate the cups. Now you have your based outer surface, which you can now spiralize. And now you have a spiral. So, and this is a seamless spiral. That's the benefit of using a spiralized node. So one thing to show you what's the difference is what will be if you do it with circles. You will have this jump and Z. So, but in the case of circles, it would be a straight jump. Here it is diagonal one. And it looks actually not that nice in the print, so I avoid it always. So now you have the spiral. You need again to set your layer height here in the spiral to the value you need. It depends on your machine, on your nozzle width, what you can print actually. So somebody which prints with clay, for example, will use much higher layer height than somebody with a normal 3D printer for plastic materials. Let's say to 1 millimeter or 0.3 millimeters. So this is already a more interesting shape than just a cylinder. And in order to make it even more interesting, you can start to add some other nodes in between. So you can, for example, modulate these circles with the modulate curve node. So we try to insert a node here on this edge, and it's there. So it's hardly visible because the amplitude is probably too low. Set it to 1. You see, it is now modulating the circles. And you see this polygon nature of the circles. You can just increase the samples and also increase the samples of the loft. So the curve is actually smooth. So, and the loft is also smooth. You need to take care of any node because each node has its own settings. So the problem is here the spiral itself. It has too few samples. So let's show it to you. It's quite a low resolution here. Just increase the sample size here. And now it's also smooth. And you can do different modulation to each circle now. So you remember we used to have some number of circles here, 100. And we put 100 circles to the curve mode with one amplitude and one frequency. And therefore it's applying the same settings to each circle. But what you can do, you can use the number series again. You will need 100. And let's say we have some small step starting with 0. And now if you connect that, for example, to amplitude, what you end up with is having 100 circles and 100 amplitudes. And this will give you different amplitude at each circle. So this is what you can play with. Of course, you need to know what you do that way, because the final amplitude will be 100 times 0.1 is 10, which is way too large. So, and you can just define some other formula, some custom expression for that, or you can use it for frequency, for example, or for something different. For now, we just do it much, much smaller, and it will create a fading effect. So you have very, very low amplitude for the first circles, and then it's increasing for the top circles. Yeah, this is what you can also achieve in the curve mode if you apply it to the spiral itself and not the circles and use fading option. So you have always many ways to achieve something. Okay, and because of this fading option, it's very easy to do directly in the curve mode. But if you want to have different frequency for each circle, so you have no other way than using this technique of different lists. So if we delete it, let's deactivate spiral for now because it's taking time. If you connect it to frequency, you see now it's very low because the final frequency is just 1. Let's go from 1 to 100. And now we have a different effect. You have very low frequency at the beginning and the frequency starts to increasing at the end. With the frequency, you also need to be aware of that you can only have integer values for the frequency, but it's handled internally. But yeah, keep in mind. So this is how this shape would look like. Kind of strange. And this is I think the beauty of generative algorithmic design, that you can explore some designs which are surprising you at the end, because you are connecting some things, playing with parameters, and at the end you end up with some design which is somehow interesting, and it was a surprise for you because you did not plan it that way. Okay, this is the input matching by lists, so you can use that feature. So what you can do else, you can add more nodes in between. So for example, we can add a rotation here. And if we rotate, we have one value. It will rotate all circles. It does not change the shape anyhow, right? So and here you can use the same technique. You take a number range or number series. You need 100 because you have 100 circles. So always keep that in mind, that work with matching lists, unless you know what to do otherwise. And now you can create 100 different rotations. So each circle will be rotated by a different value now. So, and this is already a little bit more interesting. Yeah, you see you can combine loads of nodes together. You can chain them. You can create very large graphs. You can experiment with that. Has lots of potential for creativity. You can use, for example, twist node, and then you can rotate it somehow again around z-axis by 45 degrees, let's say. And it's doing basically the same what our rotation for each circle did. It is basically twisting. Let's try to reverse it. Yeah, it looks also like it's reversing the effect. But you can change the axis, then it will be very strange. You could not print it. Yeah, keep in mind, you can also do strange things here. If you want to play with some, let's say, organic shapes, for example. We can take the vector warp node and do some deformation with that. Here's the strength input to demonstrate what it does. So it adds some noise, in this case, to your surface. And here it changes also the bottom. And if you print, so that's one of the important things to know in using that for 3D printing, you always want to have your first layers to be plain in Z. So they actually start at your print bed and stick to it. So, and in order for that, nodes which can manipulate these parts of your shapes have fading effects. So you can, for example, you can here purely deactivate Z deformation in the vector warp, and already you have some kind of organic deformations here with, I guess this is spelling noise. Yeah, it's spelling noise in all directions except Z, and this prevents breaking of the first layers. But sometimes you want, if you want to do something non-planar, you want to have deformations in Z, but you want to fade in Z, so the first layers are not affected by that. And if you do that, you see you have in the top layers, you have the deformations in Z. So you could probably already print that if you have enough clearance with your nozzle. So maybe it's too much, you can decrease it a little. So, and with that you could already print something like this. And at the bottom it starts at layer height at 0. So it is not a problem at all. Yeah, what is important to know here, we are doing this deformation on the mesh, and we cannot print the mesh. So if you try to spiralize that, it will fail because it cannot create a proper spiral of that. It will miss some surfaces because of this non-planar nature. So, and the better way to do it, so to create your spiral first and then to deform the spiral already. This is also one thing which you want to keep in mind. You can do here in Gerridaj things in many different ways to achieve the same result, and there are of course better and worse ways of doing that. So keep in mind you can be more efficient by doing some expensive operations, for example on one shape, and then distribute it later and make copies of that instead of copying one simple shape and then deform hundreds of them, for example. And like in this case, if you need some non-planar print paths, then first generate your print paths and then deform already the paths, because this will work the same way. And now you can print it. And you see, in this case, you don't even need some compensation for different layer heights. What it does, you see, the distance between some layer lines is increasing, and the distance between others is decreasing. And if you print it with constant extrusion, you will end up to less extrusion in areas where it is further apart, and too much extrusion where the lines are squeezed together or too close together. And we have, in this node, we have compensation for that. You can activate the adjust flow rate, and this has different settings of how accurate the calculation is. If you turn on the maximum, it will take longer to calculate, but it will try to calculate the most precise at any point. So it will calculate the flow rate adjustment at any point, which takes longer. If you do it in a different settings, it will skip some points and use interpolation. So it will assume that the points that are close together need same extrusion. So this works quite good most of the times and is much faster. And if you try that now, you see it visualizes also in areas with this blue color, it will generate less extrusion. And in areas with red color, let's say, to see it more clearly, so you can adjust here the intensity of the flow compensation. And it's just by testing out manually, because it's different from printer to printer, from nozzle to nozzle. You can, at least for now, it can be not exactly mathematically precise. It is not, so you need to experiment a little to find the right values. And you can just increase the intensity of compensation here. And it will extrude even less in the areas where the lines are close together, and even more where they are further apart. So, and here you see it better. So in the blue areas we have less extrusion, and the red areas we have more extrusion. And this is what you already can print in non-planar way. So that easy. Yeah. And if you want to do something special and you know some math, you can always specify your own vector field for that, for deformation, or your own displacement functions in each direction, and just put it here, and it will create the deformation for you. Okay, this was vector warp. So this is already quite long, I guess. Maybe we should come to finish here and generate some G-code from here. Yeah, as always, you need a machine node. You need to bring your print paths, your geometry, to the print area of the machine. So for that, you use a translate node and just define the translation. set up your print bed, connect, and try to print. You see you have here some warnings. These are some safety measures in order to protect your machine from non-printable G-code. This means the geometry is not exactly on the print bed in this case. So if you look from the top, we are too far outside. So we need just to move a little bit more into the print bed, and now it should be fine. So file is ready, and you can preview it, and this will be now significantly longer than our first example with 5 points. So you see we have here 165,000 points. So this is a lot, but your printer has no problem with that. It's a machine, has no emotions, no knowledge of boring, so it will just go from point to point and do the work. So, and what I explained to you about this continuous Z change, this is what you see here. The Z command is not like a normal slicer. Okay, in the VS mode, normal slicer do that as well. But in normal layer by layer slicing, you have Z jumps, which are much larger than that, and they are not that frequent. And here you have at any point or any second furrow point, you have a different Z height. So this creates a print path which has no seams. And that's it. That's your G-code. You can download it and print it. It looks, if you are working for the first time with the tool or such kind of tools, with these nodes and all the settings, it may look a little bit intimidating at the beginning, but once you've played around a little with that, it actually becomes quite intuitive and quite easy to use. So I encourage you to just try it out and see the examples. Maybe if you do not trust the G-code right away, you can start just with the meshes. So for example, you can forget about this spiral thing and the machine node. You can just take your mesh and use export mesh node. And with that, you can download your STL and slice with any software of your choice, any slicer of your choice. So, and this feature is fully free and will also remain free. So exporting meshes, you just need an account here, and you can create parametric designs, export as many meshes as you want, no restrictions here. The only thing which requires buoyancy or credits is the machine node and the graph mapper node. These are the only two premium nodes of all the nodes. So I have shown you only a few of all the available nodes in the software. You will notice there are quite a lot more of them. For example, you can also load different SVG from a different software. So you can import an SVG and then you have a curve from that, and then you can design something with curves which you created in a different software, for example, Inkscape, or I don't know which other software you might use for create some vector graphics, so etc. You have lots of possibilities here, which I will explain in different videos. This one should be an kind of introduction how to actually use the tool to design something, because I tried to explain each node in standalone. This is probably too abstract, and yeah, I noticed many of you need the actual information. How do I do a concrete thing here, or a concrete shape, etc. There will be more videos on working with the tool in the future. So for now, I would say I'm done with most important things of the programming. So it works it's actually in active development now, but most of the things work quite stable now, so it's very useful already. I will still proceed with development. I will still read all the feedback I get and try to implement more features if I get feature requests from you, and also fix the bugs if you find some. So please reach out to me if you find any issues, if you see there are some missing important features, etc. I will try to implement that. And yeah, for now I will take more effort into making tutorials of actually how to use the tool. So please, if you have some certain needs and you want to see a special tutorial about some topic which is interesting to you, write it down in comments so I know what I need to explain first. You can also say what I need to improve in my explanations. Maybe you notice I do it without a script, so I just talk what comes in my mind. It's not always very structured that way, I know, but it takes quite a lot of time to prepare it with a script and do it very organized. So I try that way first, and if it's too hard to understand, then please let me know. If it's too unstructured and you need properly structured step-by-step way of a tutorial, then I will do that as well. I hope that this improvisation style will still be helpful for you, and you can understand better how to use the tool to actually create something with it. Also a good way to learn how things work is just to look into examples in this community public projects. you will get some understanding how things work. So for example, if you look into that, it's kind of a lampshade, which is not easy to print, I guess, but you can try. You can change the design here, and if you see how it's done, if you load it into the editor, then you can see all the nodes. And the first thing what you can do to learn how things work here, just do the following. You just deactivate the viewer node. You can hit M on the keyboard to deactivate it, or you can disconnect it, just how you want. And then go to the beginning and start with the preview, how it started. So the first thing you see on the left side, you have here some kind of rectangle. And if you activate it, it's very small rectangle. And that's a rectangle with rounded corners. Okay, so this is one of the base shapes. Okay, you know you need that. And then you have here sweep. So the sweep creates this one piece. Okay, then you know that. And from here, you see the sweep actually takes a path curve. And the path curve is coming from here, from curve mode. Okay, what is that? So this is this path. And this one was created from the curve itself, which was not modulated. And if you go inside, you see, okay, this is actually your base curve, which you can modify here if you want. So let's say we want to change the shape somehow. And now the curve is changed. And this curve is modulated. So you see, and just add some sine wave to the curve. We've connected number values, so you can increase the amplitude here or frequency, and this change your mesh in this case. So we just get it from the rectangle and the curve using sweep node. And then we have a mirror node here, which duplicates the curve by mirroring it on the other side, and a group node. So now the next thing what we do, this is what I told in the video in the beginning or in the middle. If you need to sweep here, you do it with one curve and then you distribute, and then you have many. It is much more efficient to put the curve into distribute first and then to do the sweep 33 times or any number of times as you count set, because it's much faster. You see, it's because the nodes before are not calculated anymore. So now you're just getting copies of that. So take care of that to create efficient workflows. And okay, you see in the example, we had also some base, and the base is in this top area. You see it starts with a circle. It's extruded. And we have a circle again. It's subtracted. So it creates a hole. But we have also some more subtraction here. And we subtract these shapes to create this kind of strangely shaped pattern holes here. And this creates the base of our lamp. So you can use, as you see, normal booleans here. So this is like in standard cut operations, so cut, union, etc. But you see, I use here group a lot because group is only grouping without to perform the actual union, and it's just instant operations, very fast. For 3D printing, it does not matter whether the shapes is actually unified or not, because the slicer, if you download the STL and slice it, the slicer just works with that the same way. So it does not make any difference whether it's union or just a group. So if you don't need a union, just avoid it if you just need an STL. And that's it. From examples, you can learn that way how they work. Of course, it's sometimes not enough to see to the node graph from the outside. Sometimes you need to go into the settings, like for example here in this distribute node, you don't see that this was a circular distribution and which settings were used in the node, etc. So you can just go into the node and see which settings are there, and then you can start to play with it. You can start to connect some other number sliders or some other inputs, or insert some more nodes, etc. And this is also a good way to learn the basics of how to work with the software. Yeah, and I would like if you created some design which you want to share with the community, I would also like to encourage you to publish it to the community. This is this button here. It's publishing to project. You can not publish without the viewer. Okay, you need to connect the viewer, activate first, then connect it. So now you can publish, and here you can provide some basic information to that. Let's start just dummy here, so it's fast. And after new description, so if this is done, you can here define which inputs, which settings to expose to the user in the published project. So normally you want to have almost all of the number sliders, so you can select all of them. And then in the sweep node, this cap and cap start you don't need. These are the settings which are closing your mesh, so it's watertight. In the curve mode, you need the modulation type. Lots of times you can include the bulk, etc. You don't need nothing from the group. Then you go to next, and you see here, this is your setting of what inputs and sliders are exposed to the user. Here you can create some design already for a picture, because if you hit publish here, it will take a screenshot of that and publish the project. And if you do that, and if you share your design later on and receive likes to that, you will earn buoyancy and credits on the platform, and this will allow you to use premium nodes without any subscription. So this is like a contribution-based premium usage, so to say. So if you do that, you can use all premium features with buoyancy by just publishing workflows and receiving likes on them. So any like received in your design will give you 1 credit, and this allows 1 G-code to download with machine nodes. So if you create something which people really like, then you will get lots of buoyancy, and then you don't need any subscription. So this is something I think it's quite fair, because I need to earn something with this project in order to improve that, but I also want to keep it useful for all the people which want to use it as free as possible. So there is a 100% free way to use it without any restrictions by just contributing a little to it. That's it. There are also some options here to share public projects and to embed it. So if you have your own website and you need some kind of parametric design, parametric shape, I don't know, can imagine to design here some gridfinity or something, and then you can copy that embed code and just integrate it into your own website. This is also a feature which was included in the last weeks into the platform. So okay, with this, I would say now it's for sure enough of talking for this video introducing how to design shapes in Gerridaj. If you like it, please do, you know what to do with it, like, subscribe, share, etc. Give me any feedback about the software, about of the tutorials, what shall I improve, so don't hesitate with the critique as well. I appreciate it truly, because I want to improve, and I think it benefits all of us if we are open for feedback and improvement anyways. So thank you for your time, for hearing me, and I hope the next video will not take that long, and I can explain more of the nodes and maybe create more of advanced designs, etc. So again, thank you and enjoy. See you next time. Bye bye.